All right. Distance vector routing. So distance vector routing is a unique routing protocol where you send packets within an autonomous system. Okay. So it's basically routing packets inside a LAN network. Let's say what is going on is, let's say there are a few routers. Consider all of them as routers, and they are all interlinked. Okay, this is the way they are interlinked. Okay, and this is A, this is B. Let's say. Okay. Now what we have to do is the A wants to send a packet to B, but it doesn't know how to send it. We have to figure it out. It has to send through some way, but it has to figure out how to send the packet to B. In distance vector routing, what happens is each router each router maintains a table saying to reach each others, to reach let's say this is C, D, E. The each router in the network maintains a table called routing table. Here it stores to reach A what should I do, to reach B what should I do, to reach C what should I do, to reach D, to reach E. What it says is to reach A how much cost it takes. To reach A it takes 0 cost because we are at 0, and to reach B, let's say it takes X cost. Let's say it takes 5 cost. To reach C it takes 3, to reach D it takes 2, to reach E it takes 3 again. This is the cost to reach B. That is, if A wants to reach B, it can reach in 5 cost. And what the next entry is next entry is what is the next point I should send the data. See, A can reach B through this way, this way. There are so many ways to reach B, right? We don't care about that at all. What A cares how much cost it takes to reach B, and what is the next point I should send the packet to. Let's say here it is D. It just says D. To reach C, you can directly reach C. Let's say this is cost 5 and this is cost 2 and this is cost 1. Now A can reach C in 5, or A can reach C through D. So what A says is I can reach C in distance in a cost of 3, and I can next hop I have to send the packet is D. So something like this. Each router in the network maintains this table independently. That is basically what distance vector routing is. The shortest path to each node is calculated by something called an algorithm called Bellman algorithm. All right. What Bellman algorithm says is the minimum cost to a node is the minimum of the distance between myself and my neighbors and the neighbors and the node. Let's say this is A, and A has, like, let's say 4 neighbors, 1, 2, 3 and 4, and we don't know how they reach the destination, but they somehow reach the destination. They reach the destination of B, and let's say from A to C1, C2, C3, C4. From A to C1 the cost is X1, and A to C2 the cost is X2, A to C3 the cost is X3, and A to C4 the cost is X4. And from C to B, we don't know how it does, but it somehow does it. So C says that from C to B the distance is let's say K1, this is K2, this is K3, this is K4. Okay, what Bellman Ford algorithm says is my minimum distance, the shortest path for me is whichever is the minimum of x1 plus k1, x2 plus k2, x3 plus k3, x4 plus k4. So that is basically what Bellman Ford algorithm says. In Bellman Ford algorithm, when used for distance vector routing, we should take care of a few things. In the previous Bellman Ford algorithm, we said the cost is x1, right? When Bellman Ford algorithm is used for distance vector routing, the cost is hops. So if the packet jumps from one node to another, it is called a hop, and each hop is of cost 1. So each hop will be of cost 1, and each router should maintain its routing table individually. So each the cost is hops, and each hop will cost us 1 unit, and each router maintains routing table individually. And the next thing is each router will keep three information. So each router keeps 3 information, that is destination, cost, and next hop. All right, so these things we should take care of when we are using Bellman Ford algorithm for DVR. Also, one more thing is, as soon as we find a short route, we should convey that information to our neighboring routers so that they can also convey information, so that they can also update their routing tables for a more efficient transmission. Let's see an example for this. Let's say we have routers. So everything is connected. Let's say these two are connected. Now we have a routing table. Let's say this is A, B, C, D, and E. And this is the routing table of A. And A says I can reach A at a cost of 0 through, I don't have to next hop anywhere, so it is null. And I can reach B at a distance of 1, and the next hop is B. To reach D, I can do it in a cost of 2, and the next hop is D itself. To reach E, the cost is 3, and I can the next hop is D. To reach C, I can do it at a cost of 4, and the next hop is D. This is the routing table for now. And suddenly another router joins, and now it is connected in this way. Okay, this is connected, it is connected in the middle. Now if there is a more efficient route, then the nearby router should communicate to each other that the routing table is updated, there is a more efficient route will go through this way, so that each other router in the network can update their routing tables. So this also we have to take care of when we are using when we are using DVR, distance vector routing. Yeah, that's basically it. We'll also see something called two loop, two node instability. The problem with DVR is it is said that good news fast and bad news is slow. It is because we said that whenever a new router joins, or when there is a more efficient path, whenever there is a more efficient path, we communicate that information throughout the network, and the routing table is updated instantly, right? So that is why good news propagates fast, but the bad news propagates really slow. Let's take an example for that. That example is called, let's say, two node instability. Let's say there is an X, it is connected to A, and this is connected to B. All right, each of a cost of 1. Now B has its routing table saying that B has its routing table which says that I can reach A at a cost of 1 and the next hop is A. I can reach B myself at a cost of 0 and the next hop is trunk. I can reach X at a cost of 2 and the next hop is A. This is a B's routing table. And A's routing table will be like, I can reach A at a cost of 0 and there is no next hop because that's me. I can reach B at a cost of 1 and the next hop is B itself. I can reach X at a cost of 1 and next hop is X itself. Now, how B calculates this table is, how B calculates its table is, A says to B, I can reach X at a distance of 1. That information, this information is conveyed to B, and so that B says, okay, I can reach you at a distance of 1 and you can reach X at a distance of 1. So the total distance will be 2 and I have to send the packet to you. So this is how the routers are updated. Now what the problem is, the problem occurs when, let's say, this connection is broken out. Okay, this connection is broken out and now the distance to X is infinity because we are not connected to X. Now what happens is, now this B is advertising that I can reach X at a distance of 2. I don't know if this table is visible for you, so I'll redraw this table a little above. This is B's routing table. Okay, A at a distance of 1 and the next hop is A, X at a distance of 2 and the next hop is A. All right, we'll erase this. Okay, so now the connection got destroyed and A is updating its table to infinity. It says that I cannot reach X at all. Now what can I do? At the same time, B is advertising its table to everyone, right? And B is saying I can reach X at a distance of 2. Now suddenly A sees that and it thinks, okay, if I send the packet to B, then he will somehow reach X. I don't care about that, at a distance of 2. Since this route is infinity, we say that, okay, to reach X, what I have to do is I have to send my packet to B, and B will reach X at a distance of 2 and I can reach B at a distance of 1. So the total distance will be 3. All right. So previously it was 1 and then after the connection broke it was infinity, and A saw that B can reach X at a distance of Now it says, okay, this time I'll reach X through B. Now B sees this and it says, okay, I was sending my packet through you. Previously you said you can reach at a distance of 1. Now you say you can reach at a distance of 3. To reach you, I need a cost of 1, right? To a distance of 1. So my cost will be 4. My cost will become 4, right? Because A takes 3 units to reach B, and I can reach A at a distance of 1. So the total distance is 4. Now again, A sees this. Okay, you previously you said you can reach at a distance of 2. Now you are saying you can reach at a distance of 4. Now this is updated to 5. All right. Again, this goes on and this sees this and it says, okay, I can reach at a distance of 6. Then this takes 7, and it keeps on increasing. This packet goes back and forth, back and forth, back and forth until both of them reach infinity. Remember this infinity, whenever the connection got disconnected, that information is not spread very fast, right? This took infinite amount of time so that each router can say that we cannot reach X. So bad news propagates slowly. That's the main problem of distance vector routing. There are few ways we can solve this. We'll see how to solve this. The first solution is defining infinity. In the previous case, this was very slow because it took infinite amount of hops till we knew that we cannot reach X at all, right? What if we say infinity is equal to some number? Let's say infinity is equal to 16. If there are more than 16 hops, then we say that the destination is not reachable. So this is much faster. So we can define infinity. Then what we can do is we can hide information. What hiding information is something like, yeah, technically it is called split horizon. Split horizon is hiding information. Remember, we got disconnected and B said that I can reach X at a distance of 2. That is the main reason for A to update its routing table to from infinity to 3, right? What if B hides this information? Because it came from A, so there is no point in sending this information to A because it will create unnecessary chaos. So B will not send this information at all. So the horizon is split and only this information is sent to A. So that is split horizon and that is hiding information. You can also do it in a third. It is a slight modification of split horizon. It is called split horizon with poison. All right. This routing table is not valid for infinite amount of time. Each router in this network runs a timer after which the routing table expires, right? Now by split horizon, if B is not sending any information about X, now this creates unnecessary chaos, right? A doesn't know what is going on, so it cannot make a decision what is going on. So what we do is along with sending this information, we'll also say don't use this. We'll send it with a poison. Don't use this. We'll send it with a flag. Don't use this because this route came from you. So there is no point in using this. So this is called split horizon with poison. Yeah, that's it for solving the problems of distance vector routing. All right, we'll recap it once before we end this video. Distance vector routing, it is a protocol to, it's not a protocol, it's a way to send packets from one router to another. This works on Bellman-Ford algorithm. Bellman-Ford algorithm says that the minimum distance between A and B is the minimum of the sum of my distance to the neighbor and the neighbor's distance to the destination. So that is Bellman-Ford algorithm. For Bellman-Ford algorithm, yeah, That's Bellman for algorithm. And when we are using distance vector routing, we should take care of a few things. Each router should store three information, that is the destination, the cost to reach the destination, and the next hop. And the cost in this network is the number of hops, and we also can define infinity. And whenever we get some information, we share it with the neighboring router so that they can also update their routing tables. The main problem with DVR is good news travels fast and bad news is very slow. We saw that with the help of something called two-node instability, in which one of the routers got disconnected. This path was updated to infinity, and then A saw that B can reach X at a distance of 2, and then A updated its routing table to route the packets through B. And B, when A updated, it also updated, and the updation kept on happening till both of them reached infinity. This took a lot of time, and so to solve this, we proposed a few solutions called defining infinity, split horizon, and split horizon with poison. So we, instead of going for infinite hops, we can stop the hopping at a hop of 16 or 32 or any numbers. That fastens the process. We can also use something called split horizon. That is, we need not advertise this route to the nearby router, so that many confusion is avoided. Or split horizon with poison, what we do is we advertise the route, but along with it we send a poison saying that don't use this route because it came from you, it's of no use to you. All right, that's it for distance vector routing. In the next video, I'll we'll talk about RIP protocol. All right, yeah, that's it for this video. I'll see you in the next one.